Hi friends, very good morning. Welcome to Anu Academy. Very good morning friends. In today's class in our channel we are going to discuss finite element methods. Okay, finite element methods FEM. So let us start today's class. If you have not subscribed our channel, please subscribe our channel. Please like and share our channel. Okay, so now we will start today's class. So in today's class we will start with the one dimensional elasticity problem, and we will come to know how problem can be selected, and with the selected problem how we can solve the finite element method. Okay, so let us start today's class. If you have not subscribed our channel, please subscribe our channel. So for this one dimensional elasticity problem, we will take one stepped bar. So we will see one dimensional static analysis of a stepped bar. Okay, so please watch the entire video, so that definitely it will be useful for your upcoming semester examination. Okay, so first we will start with this diagram. So this is our stepped bar. So in this stepped bar, how we are plotting the elements, and how we are plotting the nodes, all these things we can understand with the help of this stepped bar diagram. Okay, so here this is our area 1, and Young's modulus. Okay, we can say modulus of elasticity area 1, and modulus of elasticity 1, and here this is our area 2, and modulus of elasticity 2, and this is the point load. This is the point load P. Okay, this is the point load P. So here we can understand the it is a introduction of a stepped bar subject to axial load P. Okay, subject to axial load P. So now this we have plotted now. So here this is the axis. Okay, now we will plot the length for the given stepped bar. Okay, so this is the, how we can see, this is the length for this stepped bar. For this one, this is our first L1, it comes under L1, and this is L2. Okay, L1 and L2. Okay, so this is small introduction. As I told you, this is area 1, area 2, this is modulus of elasticity 1 and modulus of elasticity 2. This is length 1 and length 2, and P is the point load. So the entire diagram which we can understand, a stepped bar subject to axial load, subject to axial load P. Okay, so once like that we will get the diagram. First thing is we have to understand the diagram. Until and unless if we cannot understand the diagram, we cannot go for the solution. Okay, understanding the diagram means we have to read the question properly, then only we can go for the solution. Okay, so now we will see the discretization for the bar. Okay, see how we can understand the discretization is, see, we have to select how, first we have to plot the elements, and next we have to plot the nodes. Okay, now the meaning of discretization is we have to plot each and everything acting on the given member. Okay, so first we will draw this discretization. Here see carefully how I am drawing. This is the diagram which represents the discretization. In this diagram we are going to plot first, this is the first element and this is the second element. Okay, so this is the first node, this is the second node, and this is the third node. Okay, and we know this is L1 length 1, and this is L2 length 2. Okay, so next we can see, we can plot the displacement here, that is q1, and this is q2, and this is q3. Okay, so like that we can understand this, the concept of this discretization. Okay, and now we will select one problem. With this problem we will come to know how we can use or how we can apply this finite element method for, especially for one dimensional elasticity problem. Okay, so I will write here the problem. So and I will write the problem and we will see the solution also. Okay, see, so how we will, whatever the data is given in the problem, we will start. See, we should have E1 is equal to, E2 is equal to 200 gigapascals. Okay, and area 1 is equal to 2, area 2 is equal to 900 mm square, and L1 is equal to 2L2 is equal to 90 mm, and load P is equal to 50 kilo newtons. Okay, 50 kilo newtons. So this is the basic available data for us for applying the finite element method, right? So first decision that is to be taken before solving the problem is the unit of length, whether it is in meters or centimeters or millimeters. Okay, so let us choose mm, since areas and lengths are expressed in mm. Okay, so first we have to choose these things, right? Now we'll start the solution here. So let us choose mm, since areas and lengths are expressed in mm. Okay, now we'll start the solution. Okay, therefore E1 is equal to, E2 is equal to 2 into 10 to the power 5, it's megapascals. Okay, or we can write it as Newton per mm square, right? And area 1 is equal to 900 mm square, right? And area 1 is equal to 900 means what about area 2? It is 450 mm square. Okay, area 2 is 450 mm square, and let L1 is equal to how much is given. L1, it is 90 mm. Okay, L1 is equal to 90 mm, and L2 is equal to 45 mm. Okay, I think all of you are understanding how we are taking all these things. Okay, right. Now as we are dealing with one dimensional elasticity problem by with the help of this finite element method. Okay, we will start with the element 1. In this element 1 we will calculate stiffness matrix, load vector, and for the element 2 we will calculate stiffness matrix and load vector. Okay, so we will start calculating. So we will write here element 1. Okay, element 1, right? So element 1 we have to calculate stiffness matrix. Element 1 we have to calculate stiffness matrix. It is represented as the K for element 1. So K stands for the stiffness matrix for this element 1. Like that we have to write, that is equal to modulus of elasticity into area 1 by length 1 of matrix 1 minus 1 minus 1 1. Okay, so this is for 1 2 and this is 1 2. Okay, so what we will get here, so it is 2 into 10 to the power 6. Okay, 1 minus 1 minus 1 1. Okay, so if we write these things, it will be helpful for us in framing next global matrices. Okay, now right, next after the stiffness matrix, next step is we will write the load vector. Next is the load vector. Okay, load vector for which one? Load vector, see, first we are calculating the, we have wrote element 1, right? Stiffness matrix for the element 1. So first element and second element. So first element we are writing next load vector. Okay, so we are writing now load vector for element 1. So load vector, it is represented as F for element 1. Okay, F for element 1, right? So P1 for the first element and P2 for the first element. So like that we will be writing. Okay, so this is 1 and this is 2. Okay, now right now for first element it is completed. We have written stiffness matrix and load vector, and we will write for the second element. Okay, element second element, right? Again we will write stiffness matrix for second element. Okay, so K for the second element, this is the stiffness matrix, and it will be E2 into area 2 modulus of elasticity into area 2 by length 2. Okay, so matrix 1 1 minus 1 minus 1 1. Okay, so here we have represented 1 2 and 1 2. Now we will write 2 3 and 2 3, so that is equal to 2 into 10 to the power 6 of the matrix 1 minus 1 minus 1 1. Okay, 2 3 and 2 3. Okay, now we will write a load vector for the element 2. This is the load vector. So F for the second one, that is equal to P2 for the second element and P3 for the second element. Okay, this is 2 and 3. Okay, so I think all of you are understanding. Please, if you are having any doubts, please post in the comments box. I will give you reply. Okay, now we will go for the next step. Okay, so here we have finished writing the element 1 and element 2. Okay, next step is we have to write the global matrices. Okay, so global stiffness matrix size is 3 by 3 since the number of rows and columns are equal. Okay, and to the product of number of nodes and number of degrees of freedom at each node. Okay, so number of rows is equal to 3. Number of rows means here 3 nodes are there. One is translational degree of freedom at each node. Okay, similarly number of columns is 3. Okay, so it's a 3 by 3 matrix. Now we will write a global stiffness matrix. Okay, now we will write global stiffness matrix. Okay, global stiffness matrix. Okay, global stiffness matrix. Okay, so it is represented as K. Size of the matrix is 3 by 3 is equal to, so K 1 1 for first element, K 1 2 for 1 and 0, and here K 1 2 K 2 2 plus K 2 2. Okay, and here it is K 2 3. Here it is 0 and K 2 3 and 0. Okay, so this is global stiffness matrix for given the problem. Okay, I think all of you are understanding this one. Now we will put our values in this global stiffness matrix, because here we observe that there is a summation of two terms since both elements contribute to node 2 and the node is common for both the elements. Okay, now we will go for the next step. Okay, so that is global stiffness matrix K is equal to 2 into 10 to the power 6 1 minus 1 0 minus 1 2 minus 1. Okay, 0 minus 1 1, right? So as it is, the size is 1 2, 3, and here 1, 2, 3. Okay, I know all of you how we got. I'll show you how we got this matrix. We'll go back to here. See here, for first, see 1 1 we are having 1. Okay, 1 1 we are having 1. Okay, and 2 1 we are having -1, right? And 3 1 we don't have, that way we kept 0. And next to 1 2. Okay, 1 2 we are having -1, and 2 2 we are having 1. Okay, same way here, uh, come back to here, we are having again 2 2 you are having 1, so 1 plus 1 it is 2. See, you can see here how we got this 2. It is because 1 plus 1 we got 2 by adding this matrices. Okay, and next here you come 3 3 2 we have, see 3 2 we have uh, -1. Okay, 3 2 we have -1, and 1 3 we don't have nothing, so we kept 0 1 3, and 2 3 is -1, and 3 3 is 1. Okay, 3 3 is 1. Okay, so this, from this and this we are adding, and we have framed our global stiffness matrix. Okay, so we whatever the values are not there, we are just putting it as zeros. Okay, now I think all of you understood how we got this global stiffness matrix. Okay, right. Now after getting this global stiffness matrix, next what we have to do is we have to write global load vector or force vector, because tensile load is applied to third node only. Okay, tensile load is applied to third node only. So what we have to write, next step is global, next step is global load vector, or it is also called as force vector. Okay, so tensile, because tensile load is applied, tensile load is applied to third node only. Tensile load is applied to third node only. Like that you have to write all these steps. Okay, we cannot skip any step here. So we will write now global load vector. So it is again represented as global load vector is F. Okay, is equal to, right, P2 for element 1 plus P2 for element 2. So first one we'll write here P1 for element 1, and P3 for element 2. Okay, so it is 0 0, and for the third one how much he gave the problem, it is 50,000. Okay, 50 kilonewtons, now it is 50,000, right? Next step is global nodal displacement vector. Okay, next step is global, see here, next step is global nodal displacement. Okay, global nodal displacement vector. So it is represented as Q is equal to Q1 Q2 Q3 of T. Okay, so now global or system equations, we are having one formula here. See here, global or system, global or system equations K into Q is equal to F. Okay, K into Q is equal to F. Okay, na? Global or system equations, right? Now we know what is K, we know what is Q, and we know what is F. Okay, now we have to calculate q1, q2, q3. Okay, we have to calculate q1, q2, q3, because what is q here? Global nodal displacement vector is q. Okay, now right. Now we will put the values here. So it is 2 into 10 to the power 6 for the matrix 1, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1 into q1, q2, q3 is equal to 0, 0, 50,000. Okay. Now I think all of you understood this step, how we got this step. Okay. Now imposing the boundary condition q1 is equal to 0 in the above equation by elimination approach, which was discussed. Okay, elimination approach. So we'll write the next step. Okay, now we are going to apply this elimination approach. Okay, next step, see here, imposing the boundary condition. Next step is imposing. Okay, imposing the boundary condition. Imposing the boundary condition q1 is equal to 0 in the above equation. In the above equation, by elimination approach, Okay, so what we are writing here, we have to write the same matrix here, 2 into 10 to the power 6. Okay, so what is our matrix? 1, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1. Okay, into q1, q2, q3. q1, q2, q3 is equal to 0, 0 and 50,000. Okay, so what we are doing here, what we are applying here, by elimination approach, right? What is happening here? This is, we are applying the elimination approach. Okay, first row and first column. Okay, first row and first column we are eliminating. Okay, so the reduced equations are, next step is the reduced equations. The reduced equations are, right, whatever the leftover we write here, 2 into 10 to the power 6. Okay, whatever the leftover in this matrix, 2, minus 1, minus 1, 1. So same we will write here, 2, minus 1, minus 1, 1. Okay, now it is reduced as 2 by 2 matrix, and here q2 and q3, right, and 0 and 50,000. So we can write here, this is 2 by 1 matrix, and this is 2 by 2 matrix. Okay, right. Next, what is our next step? We have to find this q2 and q3. Now how to find this q2 and q3? It can be observed from the above that the elimination approach of imposing boundary conditions, the stiffness matrix size is reduced to 2 by 3 from 3 by 3. Okay, as only one boundary condition is available in the given stepped bar problem, right? Now using determinant of 2 minus 1 minus 1 1 matrix, which is 1, we will get q2 and q3. Okay, we will get q2 and q3. So already if the given matrix is reduced, okay, we know it is reduced to 2 by 2 from 3 by 3, right? Now using determinant, next step is using determinant. using determinant of 2 minus 1 minus 1 1. Okay, so matrix which is 1. Okay, so therefore q2 and q3 is equal to 1 by 2 into 10 to the power 6 into 1 into 1 1 1 2. Okay, because it is the determinant of the matrix, right, into 0 and 50,000. Okay, now we will get the value of q2 and we will get the value of q3. Okay, now we will get the value of q2 and we will get the value of q3. Okay, so how we are getting the value of q2? It is 0.025 mm and q3 is 0.050 mm. Okay, so how we are getting, see, it is 0, so whatever the leftover, it is 50,000. So 50,000 divided by 2 into 10 to the power 6, we will get 0.025, we will get the value of q2 and it is 50,000 now, so here it will come 1 lakh. So 1 lakh divided by 2 into 10 to the power 6 into 1 will get q3, that is 0.050 mm. Okay, so we got q2 and q3. Next, last step on the one more step is there. Next step is element stresses we have to calculate. Okay, what are the element stresses we have to calculate? Sigma 1 and sigma 2. Okay, so I'll write here. We are going to calculate element stresses. What are the element stresses here? That is sigma 1, we are having, this is formula, E q2 by L1 is equal to, and sigma 2 is equal to E into q3 minus q2 by L2. Okay, we know we have the value of E, we know the value of q2, we know the value of L1. So putting all these values, what we will get? Sigma 1, it is 55.5 megapascals, and here also we know the value of E, we know the value of q3, and we know the value of q2, we know the value of L2. So we will get sigma 2 as 11.0 megapascals. Okay, now last step is there, we will conclude this problem. So reaction R1, the first row of the left hand side of matrix, right, should be equated to R1. Okay, now, so the first row of the left hand side of the matrix, right, so it should be equated to R1. So we'll write here reaction R1. Okay, so it should be equated to R1. So how will we write? Minus 2 into 10 to the power 6 into q2 is equal to R1. Okay, so what we'll get? R1 is equal to minus 0.05 into 10 to the power 6 here. So this is our reaction R1. Okay, so that's all, friends. We understood, I think, today's problem. All of you understood today's problem. Definitely you will get this type of problem regarding one-dimensional elasticity problem. Okay, so we came to know how we will get a problem, right, and how to understand the problem. The main thing is we have to understand the question. So until and unless if we don't understand the question, we cannot go for the solution. Okay, so read the problem properly, understand the diagram. Okay, how we can break the diagram, like how we can plot the area, all right, and length and elements, nodes. Okay, next go for the discretization, and next start the element 1 and element 2, start writing the stiffness matrix, load vector for element 1, and stiffness matrix and load vector for element 2, and go for proceed the problem. Okay, I think all of you understood today's problem. If you're having any doubts, if you need any additional information, please post in the comments box. Definitely I'll give you a reply. If you are not subscribed our channel, please subscribe our channel. Please like and share our channel. Okay, so please watch entire full video so that definitely it will be useful for your semester examination. Thank you very much. Thank you for watching.